So when we studied trees, then we studied things like traversals of a tree, right? So there were different traversals of a tree. There were some recursion based traversals like pre-order, in-order, post-order, and all those recursion based traversals were something like depth first search. So now we are going to learn about depth first search traversal of a graph. Okay, so how does it happen? So problem statement is very simple, that you have been given a graph. It says 0 and then 4, 5 and then 6. Let's say this is the kind of graph that you have. So basically you will have, what usually happens is that in generic trees also you would see that your input edges are given as, so the problem says that there are m edges and then there are m lines containing uv. So you will have 0, 1, you will have 1, 2, you will have 2, 3, and so on and on and on, right? And based on these things, you can make out that what should basically be the adjacency list. So based on this, you can initialize your adjacency list. So when you are scanning these m pairs, then you can put these values inside the vector of vectors. So let's say this is u and this is v. So what you can do is you can do adjacency list u. So this is a vector of vectors, and in the uth list you would want to push back this value called v. And apart from this, you also know that 1 and 0 are also connected, because 1 and 0, 1 means an edge between 0, 1 and 1, 0. So for this you should do adjacency list of u, adjacency list of v dot pushback u. So this thing you have to do for m times. Any pair that you scan, you have to push these two values in your adjacency list. Then only that adjacency list would be a proper adjacency list. Okay, so I have to perform DFS traversal of this. Now you know what is the thing. In trees there was notion of root. Root was a special node. But in this, will there be, what do you think? Will there be any root according to you? In a graph, do you have a notion of something like root? You don't have a notion of root here, because anything can be thought of as a root. I can imagine this 2 also as a root. I can imagine this also as a root. I can imagine this also as a root. So that means that I can start my traversal literally from anywhere. Okay, and for now I'm just talking about the undirected edges. I just have undirected edges. So let's say I have to perform the traversal. So you can say that it can be done in a recursive manner. So how exactly in a recursive manner? So for example, what you can do is that you can start your traversal from 0, okay? And then you can see that if, let's say, there are 2 edges emanating from it, then you can say that, hey, there will be a subgraph here. So I'll first cover this subgraph and then I'll cover this subgraph. The way you do it in trees, you say that after touching this root, I'll cover this left subtree and then I'll cover this right subtree. Same thing you can say in graph also, right? But something can go wrong over here. Yeah, loops kind of thing will happen. In trees, what happens that when you are covering this left subtree, would it ever happen that you end up touching a node from here while covering this left subtree? It would never happen. Why? Because there are no cycles. But in graphs, this can very well happen. For example, let's say you are at f of 0 and then you want to make a call for f of 4 for covering this, because there is an edge from 0 to 4, and then you want to cover this subgraph because there is an edge from 0 to 1. Now let's say there was an edge from this 4 to 1. So when you were at 4, you would have made a call for f of 5, you would have made a call for f of 6, there are edges, right? And you would have made a call for f of 1 again. Now let's say that is done, would you want to make this f of 1 call again? No, you would not want to do that, right? Because if you do that, then you end up touching that node for one more time, which was already touched. So what should the intention be here? The intention should be that if a particular node has already been visited, then that should not be visited again. Okay, that is what the intention should be. So how do I do that? A very simple way to do that is to maintain an is visited array. So I can have an is visited array, and that is visited array would be a Boolean array containing the fact whether a particular node is visited or it is not visited. So if there are n nodes, I will have a bool is visited. In fact, a vector of boolean is visited, and this will be of size n, and I can initialize everything to false. So it means that is visited of 0 is false, is visited of all the nodes is false initially, right? And then the moment I am touching a node, I convert its is visited flag to 0, and then I convert its is visited flag to 1. Yeah, from false I convert it to 1, which is true, and then I embark on my journey to other subgraphs if I see that there is a node over there which has not been already touched. Okay, so how's that going to look like? So let's say you start your journey from 0. So there was a function call for 0. Now here you will mark that 0 is visited, and now you will call for f of 4. Okay, and now you are at this 4, so you would see that what are the things that are connected to 4. So when you check the adjacency list of 4, you will find 0, 5 and 6. So first you will check for 0. Will you make a call for 0? No, because 0 is already visited. Then you will come to 5. Will you make a call for 5? Yes, so you will call for f of 5. And then, so let's say you have called for f of 5, and now when you are at 5, the adjacency list of 5 will just contain a 4. And 4 is already visited, so you will not make any transitions, so you are done. And every time what you are doing, you are printing and then you are calling. So you can do something like this. So you print the node and then you call. That's how you go on, right? So this function would print 5 and terminate, right? Now at f of 4, you had called for this 5, and now you call for f of 6. So now in the adjacency list of 6, there will just be a 4, which is already visited. So this will also not do anything. So this also terminates, and now when the control comes to here, everything is done, so this also terminates. And now you come to f of 0. So in the adjacency list of 0, there was a 4, and then there was a 1. For 4 call was made, and now for 1 the call will be made. And now this 1 will be printed, and I'll say that I have visited 1, I'll mark 1 as visited, and now I'll call for f of 2, because adjacency list of 1, it will contain 2 and 3. So now you come at 2, you mark this 2 as visited, and now in the adjacency list of 2, you will have 1 and 3. So 1 is already visited, and for 3, you see that it is not already visited, you will make a call. Okay, and now you would mark it as visited. Now in adjacency list of 3, you will have 1 and 2. 1 is also visited and 2 is also visited, so you are done basically. So f of 3 expires, and then control comes to parent. So for f of 2, 1 was already visited, so you did not call. 3 is done, so this also expires. Now this comes here. Now for f of 1, you would not make that call for f of 3, because you would see that f of 3 is visited. So this is how the DFS traversal basically works. It's a pure recursive traversal that whenever you are at a node, call your subgraphs if and only if that subgraph is not already visited, because as a process of visiting subgraph 1, you might have touched subgraph 2 if there was an edge from here to here, right? So make a call for this only by checking whether is visited of this is true or false, because if it was connected to this, and let's say this was a connected component, okay, then all of these nodes would have got touched. Okay, so your is visited vector, if let's say you are passing it in recursive functions, should it be passed by value or should it be passed by reference? It must be passed by reference, right? Because you want this function to know that what is the state of that is visited vector when these function calls have been already executed, right? So this is an important thing to keep in mind, or you can have it global. This thing is a very, very interesting thing to understand, I would say. This is basically recursion tree diagram, nothing. This is just a recursion tree diagram, because this is recursion tree of DFS, so this is called as DFS tree, and this is very, very important. DFS tree is nothing. DFS tree is recursion tree diagram of your DFS implementation on a graph, and this helps us to solve many complicated problems on graphs, which we'll see later on. Let's move on. I would just say that what is the physical significance of this in some words, because I have to come back to it after 2 days or 3 days. It basically means one very simple thing, that if let's say there are 2 subgraphs that are connected to a node, and let's say that is your source node. Source node means that node from which you are starting your DFS. If you talk about all the recursion stacks that are getting created, all the recursion stacks, then you can say that this will be the last element which will get popped from that recursion stack, because this is the source of that recursion stack. So this will call this subgraph, and any other subgraph, and only when all of them are visited, then this will get eliminated. So this is a concept of recursion, but you will see how this will come out very, very handy. Anyways, if I have to implement this DFS code, how do I go ahead and actually implement it? So let's say there is a main function. Now tell me one thing, from which node should I start my DFS? Because I have to ensure that I visit all the nodes, right? So, you know, because here this graph looks like a connected graph. So you start from anywhere, you will be able to reach everywhere else, because connected graph means that you can reach anywhere from anywhere. So I can reach from 4 to everything else, or I can reach from 2 to anywhere else. So you can make a call to any node. Let's say you make a call to 0. So you can invoke a DFS starting at 0th node, and then you have a function called DFS which just prints the nodes in some order, and it takes some node as the input. Yeah. And now what is the first thing that you should do? So whenever DFS call is made, the first thing that you should do is you should mark that it has already been visited. Okay, so you should convert the is visited flag of that node to true. Okay, and after that you should print this value, print I. Okay, so this is the first thing to be done. After that, what will you do? After that, you will iterate on the adjacency list of this ith node. So you iterate on the adjacency list if you have adjacency list with you, and then you would make call for only those things. So let's say you have M and P. So let's say if is visited of M is true, that means it was already visited, so you would not make a call there. You would make a call only if it was not visited. So how is that logic going to look like? So let us iterate on its adjacency list. So for j equals to 0, j smaller than adjacency list of I dot size and j plus plus, right? And then first you would check if not of is visited what. So what will be the jth element in this vector? The jth element in this vector will be adjacency list of I comma j, right? So only if you see that there is a node n or p which is not visited, then you would start a DFS from there. So you'd call a DFS at that node, which is adjacency list I comma j. This is how you can just go on, and this is how starting DFS at any node you would be able to print out everything. Okay, so who can talk to me about the time complexity of this? V plus E, okay, where V is number of vertices and E is number of edges. So let us all understand how this is V plus E. It is very important to understand it. Please do not mug it up. Many people mug it up as V plus E. You know, what is the standard technique that we have been using so far to figure out the complexity of a recursive code? That standard technique was simple. We first figured out how many function calls are there. If that is a recursive code, then how many function calls are there and how much time is spent at each function call. So let's say there are n function calls and each function call is doing t amount of work, then the complexity should be n into t. This is the standard thing that we have been doing so far, right? But it looks like I cannot do it here. Why I cannot do it here? It is very simple to say, because the number of iterations that happen in this for loop, that is variable. There will be so many iterations for something like 1 and there will be very less iteration for something like 5. This is the main concern that would have stopped you from telling an answer. So, and that is perfectly fine. So let's do it one by one. Can you tell me how many function calls will be there? Can I say number of function calls which would happen? That would be exactly order of V, because you are calling a node just for one time. You do not call it again if it is already visited. Okay. Now, you know, there is another important technique that you should actually learn to comment on the time complexity, and that is, I'm going to explain it in a bit different way. I can say that, let's say, number of times this instruction executes, and I'm not talking about one iteration. I'm not saying that how many times this instruction executes for one iteration, because for one iteration it will execute only for 2 times or only for order 1 time. I'm saying in the overall process, in the overall this thing, how many times this instruction would have got executed. Yeah, v into 2, which is around order of v, right? Because you print any node just once, you call for any node just once. So this instruction in the overall process would have got executed for order of v times. And now I'm going to do the same thing for this. Okay, so now tell me one thing. When you were here, you inspected the adjacency list of 0. When you were here, you inspected the adjacency list of this. When you were here, you inspected the adjacency list of this. So you inspected the adjacency list of every vertex. How many times? As many times as the number of elements in that list. So tell me one thing. So in this overall journey, in this overall recursion, how many times this would have run? This would have run equals to the number of times, which is the number of values stored in this, which is the sum of the size of this plus this plus this plus this. And what is the sum of size of all these lists, all these different adjacency lists? That is 2 into e. So from that I can say that in this entire process, this piece of code would have got executed for 2e times. Is there any other piece of code? No. So in the entire process, this instruction executed v times and this instruction executed 2 into e times. So I can say that this is order of v plus 2 into e, right? And this is a very, very important thing to understand. Now, some people eliminate this 2 because they say that 2 is very small in front of e. So they say order of v plus e. Sometimes when e is of the order of v square, let's say the graph is completely connected, every 2 nodes are connected to each other, then this will be v square. In that case, the answer will be order of v square, right? But in general, you should write v plus e because it can be a sparse graph also, right? Now tell me one thing. If you did not have an adjacency list, then what would have been the time complexity of this DFS traversal? So you have adjacency matrix instead of adjacency list. In that case, it would clearly have been order of v square. Why? Because now that previous logic of finding time complexity would have worked. That number of function calls are v, and in each function call, you inspect the row of the matrix which is corresponding to I, and that row comprises of v different values. So because to figure out that which nodes are direct neighbors, you have to check this entire row and see which cells are equal to 1 and which cells are equal to 0. So in that case, it would have been order of v square. Now tell me one more thing. Let's say you have a graph like this. 0 is connected to 1, is connected to 2. Let's say this entire thing is one single graph. And let's say you have something like this also. This is the graph that you have the corresponding adjacency list representation of this graph based on the edges that you have got. Now tell me one thing. For this graph, if you call DFS at 0, will you be able to print all these nodes? You will not be able to do that, right? Can you tell me which nodes would be printed, if at all? Yeah, you would just be able to print 0, 1, 2, 3, 4. What does it mean? It means that if you call DFS at a node, be it 1, be it 2, be it anything, then you will just be able to print those nodes which are a part of that connected component. So can I say that, hey, calling DFS at any random node and then expecting that all the nodes get printed will only work if your graph is a connected graph. That is, it just has one connected component. And if that is not the case, then how to solve it? Anyone who would like to now talk about it? So what you can do is that instead of just calling DFS on 0, you need to call DFS at every such node which is still not visited. Now how do you do that? So you can do that by using a for loop. You will basically be looping over all the nodes, all the vertices that are out there from 0 to n-1, and if you see that that node has not been visited, then you would invoke a DFS call at that node. Okay, so how does the logic look like? So you would start your journey from 0th node and you would go on till n-1, And if you see that not of is visited I, if you see that not of is visited I, then you would invoke a DFS starting from I. So let's take an example of this. So you would first see that 0th node is not visited, so you would call a DFS of 0. DFS of 0 will end up visiting all these nodes. So you would have DFS of 0, 1, 2, 3, 4, all of them as true. Now tell me one thing. If you have called, let's say, DFS of 0, then in that case, what would have happened? You would have visited 1, 2, 3, and 4. So will you call DFS of 1, DFS of 2, DFS of 3, DFS of 4? Will you do that? No. You will then call DFS of 5. And when you call DFS of 5, 5 and 6 will be visited. So you will not call DFS of 6 again. And the same thing here, when you call DFS of 7, you don't have to call DFS of 8 and 9 again, because this check would be false for those. Okay, so now my question is time complexity. Does the time complexity change for the graphs which are not connected? Will it be greater than V plus E? Yeah, so no is the correct answer. So it will continue to be order of V plus E only. And why will it continue to be order of V plus E? So it will continue to be order of V plus E for a very simple reason that whenever you are at a particular node, okay, then you basically visit that entire connected component, okay. When you visit that entire connected components, the things which are present in it, for those you would not end up calling again, right? So whenever you are at a node, whenever you see a node, there are two things that can happen. Either you reject that node because that was a part of a connected component already, or you start a DFS from that node. So for the maximum number of times you touch a node in your entire algorithm is 2 times. First time when you see that is not visited, so let's say 7 was not visited and you invoke the DFS at 7. So there your algorithm touched this 8 once. And then when you are iterating and come from 7 to 8, then you touch this 8 again, but then you leave it. So the maximum number of times you touch any node is 2 times, either while considering that in DFS of any connected component or while rejecting it because it was already a part of some connected component. So that way I can say that it would continue to be order V plus E only. So please do not assume on your own that the graph is connected or not. If it is not explicitly given that it is connected or not, then you have to use this thing. Now tell me one thing. Remember the first few parts of the class where I said that there is a magical function given by God, and that function takes a graph and tells you the count of connected components. Let's say the graph is an undirected graph. Can you implement such a function for you now, which tells you the number of connected components? Yeah, what will you do? What you have to do is, every time you call a DFS from main to here. So whenever you see that there is a call happening from main to DFS, that means that call happened because there is a new connected component which you have to visit, right? So you would call DFS from this main function only for 3 times, right? You call for 0 and then you don't call for these. Then you call for 5 and you don't call for this. Then you call for 7 and you don't call for these, right? So the number of times you call DFS function from main, that will denote how many different connected components are actually there. So you can do that in a very easy manner. You can have a count variable which is initialized to 0, and every time you make a DFS call, you can do a count plus after that, okay? And then eventually you can return that count. So this count can now tell you whether the entire graph that you had was connected or not, because if this count is equals to 1, then it was connected, and if this is greater than 1, then this clearly was not connected.